When we look at heterogeneous chemical equilibrium, we have to be a little more careful, have to take into account material balances in a way that we don't need to consider when we're looking at just homogeneous, for example, just gas phase equilibrium. And the easiest way to understand this is to look at examples. Let me write down a reaction. So we're looking at this equilibrium in which solid carbon reacts with carbon dioxide gas phase to make carbon monoxide in the gas phase. And to simplify things, we'll look at the case where we have ideal gases. And what that means is that fugacities, for example, for CO2 in the mixture, is the same as the partial pressure CO2, and likewise for carbon monoxide. So if I were to write down the reaction equilibrium expression, it would be the product. Fugacity is the partial pressure, and it's divided by the pure component fugacity. And I'm writing that down just to remind us that we're going to have to write pressures in terms of units of bar for these equations to be correct. And we have the pressure of CO2 also divided by 1 bar. And then we have the activity of the carbon, which is the fugacity of carbon at the temperature of reaction we're interested in, divided by the fugacity at the same temperature but at standard conditions, meaning at 1 bar pressure. Well, when we change the pressure on carbon, we're having almost no effect on its fugacity, so to a pretty good approximation, this term is 1, and that means this equation reduces the pressure of CO squared divided by the pressure of CO2, where we're remembering that the units are bar. So the important thing to note is, if I were to change the amount of carbon in my system, I don't change anything about this equilibrium expression. In other words, because carbon is in its own phase, a pure component, the amount of carbon does not affect its fugacity. But for this equilibrium expression to apply, carbon must be present. So, for example, let's suppose we start out with 0.1 moles of carbon solid and let's say 50 moles of CO2, and we let this go to equilibrium. Well, of course, it depends on what temperature, but let's say we're at a temperature where the equilibrium is significantly to the right. What's going to happen is all the carbon is going to react, and we're still not at equilibrium. In other words, we react a tenth of a mole of carbon, we form a 2/10 of a mole of carbon monoxide, but because of the conditions I picked, we're still not at equilibrium. In other words, we're at a condition where the pressure of CO squared divided by the pressure of CO2 is less than Ka. So in order for equilibrium to be satisfied, we have to have this ratio here equal to Ka, which would mean we need to make more carbon monoxide and react more carbon dioxide. But we have no carbon left to react, so we cannot satisfy equilibrium. Important thing to keep in mind is the fugacity of carbon is equal to pure component fugacity if carbon is present. If there's no carbon, the fugacity is 0. We can't satisfy the equilibrium expression. So this is why this is fundamentally different from gas phase reactions. If I have a gas phase, 2 gases reacting to form a third gas, I can always satisfy the equilibrium expression because I can make the fugacity, for example, of the component in denominator. If I had A gas plus B gas going to C gas, I can always satisfy equilibrium by making, for example, this number small, the mole fraction small, therefore the partial pressure, sufficiently small that I can reach the equilibrium expression, the pressure of C, pressure of A, pressure of B. I can always make it equal to the equilibrium constant. That's not true when we're dealing with heterogeneous systems. Now, other heterogeneous systems, one that's a very common example is calcium carbonate decomposing to calcium oxide plus CO2 gas. Calcium oxide being a solid, And we end up with the same issue where we could, for example, react all the calcium oxide away or all the calcium carbonate, depending what temperature we're at, and not get to equilibrium. But here's something that's important that's different. These are both solids, but we're assuming they're going to be in different phases. This is important in order to say that the activity of calcium carbonate is 1 and the activity of calcium oxide is 1, means calcium oxide is in its own phase and calcium carbonate is in its own phase. And then there's two solids that do not mix. So the takeaway message here is we have to keep in mind the material balance. Do we have enough of a component to satisfy the equilibrium expression?